Okay, so we are going to start calculus. Now, much of what we have in calculus depends on properties of the real numbers. So, we are going to start off by reviewing those properties. We already know of them, but now we are going to look at them in a much more systematic manner. So, let us start by first of all recalling what real numbers are. Real numbers are numbers that can be expressed as decimals. If a number can be expressed as decimals, then or in the decimal system, then such a number is called a real number. For example, -3 divided by 4, if you express it in decimal system, it will be this. Or 1/3 expressed in decimal system, it gives us this. Or √2 etc. The dots, the 3 dots that we see in each case, indicate that the sequence of decimal digits in each case goes on and on. That means in sequence of decimal digits means these are decimal digits 7, 5, 0, etc. These are the digits in decimal system. In decimal system we have 10 symbols, right? Starting from 0 through 9. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So they are known as the decimal digits. So the sequence of decimal digits in each case, it does not end. It goes on and on. That is indicated by these 3 dots. Okay, geometrically, real numbers can be represented as points on a straight line known as the real line. Okay, should I draw it in a free-handed manner or should I use the ruler? Okay, let me use the ruler. Okay. Now the real line, as you already know, because you have used it in drawing graphs of functions, it has the numbers like this at regular intervals, -1, this is -2, this number, for example -3/4 is -0.75, it appears here somewhere. Like that, the number 1/3 appears here roughly, and the number square root of 2, which is 1.414, almost 1.5, it appears here, say. You can also think of the number pi, which is the ratio of the circumference to the diameter of any circle. We already know from geometry that that is what pi is, and its value is approximately 3.14159 something, 2653. So 3.14, it will appear, for example, approximately here. So we find all the numbers on the real line as points. Okay, numbers can be identified with points on a straight line, and that line is known as the real line. While drawing graphs of functions, we use two real lines, one as the x-axis and another vertical one as the y-axis, and the two lines intersect at this point 0. Okay, and the arrowhead here represents the fact that in this direction the numbers are increasing. One more thing is that the symbol, this R, denotes the set of all real numbers. Okay, so that's what real numbers are. Real numbers are numbers that can be expressed as decimals, and they also have a geometric representation as points on a straight line known as the real line. Okay, now next we look at properties of real numbers. Properties of real numbers. Now the real number system, or the set of real numbers, has many different kinds of properties. Mainly it has three different types of properties. So accordingly we will present them separately. Properties of the system of real numbers fall into three categories. The first is algebraic properties, the second is order properties, and the third is something known as completeness. Now algebraic properties and order properties are something that we already know. Okay, so let us see what they are. The algebraic properties of real numbers say that we can add, subtract, multiply, and divide except by 0 in the system of real numbers to create more real numbers. Obeying, okay, let me put some ink. So you can add two real numbers, subtract one real number from another, multiply two real numbers, and divide one real number by another except by 0, of course. And these things, obeying the usual rules of arithmetic. Usual rules of arithmetic means the rules of arithmetic that we are already familiar with. For example, while adding two numbers, we know that we can change their order of the summands 2 and 3. If you add 2 with 3 or you add 3 with 2, you get the same result. Such rules about which we already know and we are very familiar, in fact so familiar that we unknowingly use the rules all the time while we perform arithmetic with real numbers. So that's what algebraic properties of real numbers say, roughly. The usual rules of arithmetic, we can in fact give a list of such rules, but we already are familiar with them and we don't bother to list them here. If we ever need those rules specifically for some purpose, then we will recall them then and there itself. Okay. The order properties of the real numbers are as follows. Rules for inequality. Inequality or inequalities? Order means an arrangement of the real numbers where something is greater than some other number, some number is less than some other number, this number comes first, after that another number comes. So that is ordering of the real numbers. And we already know there is a way of doing that. We know that 2 is less than 3, minus 1 is less than 0. So using this concept, we order the real numbers. And this greater than, less than, these things give rise to inequalities as opposed to equations which arise from the equality symbol. From the inequality symbol, we get inequalities. So there are some general rules for inequalities, and the rules are as follows. Let, in fact we will need 3 real numbers now. Let A, B and C be real numbers. The first rule is, if A is less than B, then A plus C is less than B plus C. Adding a real number on both sides of an inequality does not change the direction of the inequality. It stays like this. It does not become this. Okay. This C can be any real number. Number 2, if A is less than B, then A minus C is less than B minus C. Instead of adding a real number, you can also subtract a real number from both the sides. That also will keep the direction of the inequality same. Number 3, if A is less than B and C is greater than 0, then AC is less than BC. If you multiply both sides of an inequality by a positive real number, then the direction of the inequality does not change, which in short we say like this: the inequality does not change. Of course the inequality changes. This is one inequality, this is something else. It's the fact that A is less than B. This is another statement which says that AC is less than BC. But inequality does not change usually means that the direction remains the same. In that sense we sometimes use that phrase, inequality does not change. Okay. Number 4, if A is less than B and C is now less than 0, then BC is less than AC. In this case the direction of the inequality has changed. In fact, if we wrote this thing like this, AC first, then it will look like this. Same thing, but we decide to write BC on this side and AC on that side. So the inequality was like this, now it is like this. This is sometimes expressed by saying that multiplying an inequality by a negative real number reverses it. It changes the direction. Since it will either be in this direction or that direction, I mean the greater one will either be towards the right or towards the left. So here that has changed towards the left hand side. And note that in case of addition we don't have to think of what C is or what its sign is, that is whether it is positive or negative. But in case of multiplication we have to carefully notice that unless it is positive, you cannot just simply write like this, multiply both sides by C and keep everything else as such. If C is negative, then it will get reversed. In particular, if C, in place of C, if you take -1, what will then happen? If A is less than B, then suppose in place of C you have taken -1, then this will become -B and this will become -A. So that means if A is less than B, then -A is greater than -B. Okay, so this is a special case of this. Then number 5, if A is greater than 0, then the reciprocal of A is also greater than 0. Okay, it's not less than 0. Keep in mind, okay, don't confuse this one with this one. Okay, they are two distinct things. This involves taking minus, that reverses inequality. However, this involves what can I say? This is, should I say such things at this stage? No, it's better to just keep things simple. What I am trying to say is that if you take minus, then the inequality gets reversed. But if you take reciprocal, this is also some sort of inverting. No, this is inverting the sign, and this is inverting the number with respect to multiplication. 1 by A, that does not reverse the inequality, that keeps the inequality same. And one more is there, 6. If A and B are either both positive or both negative, and A is less than B, then 1 by B is less than 1 by A. Okay. Now here also we are doing something just like taking minus. Here we are inverting the elements. We have to keep in mind, okay, in this case inverting gives us an inequality which changes direction, which gets reversed. Had we written like this, 1 by A, then the inequality, you can clearly see the change in its direction. But the thing that we have to keep in mind is that either A and B, we will have B here, no? Either A and B are both positive or both negative. That means they have the same sign. If we have one of them positive and the other negative, then this rule will not work. If that happens, if they have the same sign, then if A is less than B, then 1 by B will be less than 1 by A. Okay, so these are ordered properties, or in other words, rules for inequalities. This is the second category of properties. The first category is algebraic properties, the second category is ordered properties. Now there is that third thing which is known as completeness. The completeness property of the real numbers is more, or I should write deeper, and is harder to define precisely at this stage. The third category of properties is the completeness property. Note that these are things about which we already know. This, however, is something about which we don't know. Okay, we will know it in more advanced courses. So it's much deeper than the algebraic and order properties, and it's harder to define precisely. Of course, it can be defined, but at this stage it cannot be defined. It needs some tools and some things with which we are not familiar yet. Roughly, however, we can say something about the completeness property. Roughly speaking, it says that there are enough real numbers to complete the real line. In other words, it says that the line that we draw while talking about real numbers, and we call it real line, there are enough real numbers so that every point on the line can be given a real, can be identified with a real number. You will never encounter a point on the line which does not correspond to any real number. You will never encounter that. However, the system of rational numbers, we will see what rational numbers, or we already know, but in this discussion we haven't yet seen what rational numbers are. The system of rational numbers is not like this. It's not complete, in the sense that if you identify only the points on the line that are related to rational numbers, then there will be some points which cannot be identified with any rational numbers, and they are, you already know, are called irrational numbers. The fact that such numbers exist prevent the system of rational numbers from being complete. Okay. Real number, real line, in the sense that there is no hole or gap in the real line. These terms are not mathematically precise, they are just here for us to get a feel for the thing, to roughly understand what's going on. That's why they have been put within quotes. Okay, within quotes. And why do we need this, by the way? I mean, is this property just simply something that the real numbers possess, or do we really need this property? It turns out that we really need this property, because otherwise there is no necessity for working with real numbers. Now, rational numbers are much easier than real numbers. We could have worked with them also, but unfortunately many of the theorems of calculus would fail if we don't have this completeness property in our number system. many of the theorems of calculus fails to be true if we don't have the completeness property. However, a proper discussion of this property is best saved for a more advanced treatment of calculus, and we will not perceive it. That means we don't have to bother about this property. We just know that it is there. So it is something which we don't know precisely, but we roughly know. It says that there are enough real numbers to fill the real line. That's all we want. We need to know. And as opposed to this, there are not enough rational numbers to fill the line, to fill the geometric straight line. Okay. We will not pursue this matter here any further. Okay, so these are three categories of properties for the real numbers. Algebraic properties, which roughly say that we can add, subtract, multiply and divide. We can perform these operations within the system of real numbers. Division by zero, of course, is not allowed, to create more real numbers, obeying the usual rules of arithmetic. The order properties tell us the basic properties of this order relation, greater than, less than, that relation. And completeness is something which says that there are enough real numbers to fill the real line completely. Okay. Now let us look at subsets of R, that is subsets of the set of R, set of real numbers. We identify three important subsets of R. Number one, the natural numbers namely these numbers. Number two, the integers namely And number 3, the rational numbers. A real number that can be expressed in the form m divided by n as a quotient, where m and n are integers